Okay, in today's lesson we are going to talk about vectors. Many times we hear about things that are scalar quantities that simply tell us a quantity without direction, for example 45 pounds. Today we're going to talk about vectors, and vectors are line segments with a magnitude or a length and a direction. And an example of that would be what we've seen with our bearings problems, such as 55 miles per hour east. I like to think of vectors as an ordered pair of movement, not just as a fixed location. So if we look at this example below, we will see 4 points. If we were to draw a quick sketch of a graph as to where these points would be, we would see point A right here, point B down here, and point C way up here, and point D right about there. Now, if we were to draw a vector AB and describe it using vector notation, vector AB would start at A and it would end at B. So we say that point A is the initial point, and we say that point B is the terminal or ending point. Now, whenever we write our vectors, we are going to write them with angled brackets, and we are first going to have the horizontal movement and then the vertical movement. So if I were to write vector AB, we can think of this one of two ways. The first way we could think of it is how far we move to the right, because this vector does go right and down, and it moves to the right 4 units. And then it moves down from 1 to -4, it moves down 5 units. You can also think of this using arithmetic, and you can do the terminal point minus the initial point. So you could do 7 minus 3, and then -4 minus 1. So either way you want to set it up, it doesn't matter, as long as you remember that you are always doing the terminal point minus the initial point to describe the movement for the vector. Now, if I were to talk about the idea of opposite vectors, in this case, these are two vectors with the same magnitude, which means that they are the same length long, and opposite directions. So if I were to go ahead and find vector BA, in this case that would be traveling from point B back to point A. So the length is along, but the direction is different. So now instead of going right and down, this vector goes left and up. So we would describe this vector as -4 moving 4 to the left and 5 moving 5 up. All right, in order for two vectors to be equal, these are two vectors with the same magnitude and direction, but not necessarily the same initial point. So if we look at the 2 points that we had above, point C was 5, 7, and point D was 9, 2. If I were to find vector CD, I could find this by doing, again, my terminal point minus my initial point. So 9 minus 5, 2 minus 7, and that would give me 4, -5. And for -5, this is the same as the vector that I had up here for AB. However, if we were to look at these two vectors on the graph, and if we went up here and looked at vector CD, CD is way up here. However, these two vectors have the same movement, visually they look parallel, the same length, therefore they are equal vectors. So equal vectors are vectors with the same magnitude and direction, but not necessarily that same initial point. Okay. When we talk about magnitude and direction for our vector, you want to think about the magnitude or the length is basically how long that ray would be if you were to figure it out on a coordinate plane. So for example, if we have this vector xy, if I were to graph this, vector u would move x units over, and it would move y units up, and that vector would be right here. So we could think of this side as having x units long, and this side as being y units long. Therefore, the magnitude for that vector, or the length of that vector, is found by doing Pythagorean theorem. Now, I want to make sure you guys understand that this notation is not absolute value. And every year, students will ask me if they're supposed to take the absolute value of a vector, and that is incorrect. That is the magnitude of the vector. So if we look at problem A down here, we want to find the magnitude and direction. We'll do that next. The magnitude of this vector. Basically, what we are going to do is the square root of -5 squared plus -12 squared. And hopefully we recognize this 512 to be a triple, and therefore the magnitude of the vector will be 13. Now let's talk about direction. Direction is going to be the angle that is made with the x-axis. Now when we want to find the angle, we are going to use our tangent ratio. The reason why we use tangent is because we know the x and the y values, the x and y movement, based on the vector notation. The key thing, though, is to make sure that you are giving the angle in the correct quadrant. And we can tell this based on the positive or negativeness of x and y. So if I look at vector u over here in problem A, since both x and y are negative, I know that I'm in quadrant 3. So if I do tangent of theta equals y over x, I'm going to get a positive value. And after I plug this in the calculator and do tan inverse in degrees, I will get 67.38 degrees. However, I know that that's not the right quadrant for this angle, and I need to add 180. So my overall angle is 247.38 degrees. So magnitude and direction. Go ahead and try part B, and then unpause the video when you're done. In part B, we go ahead and do our Pythagorean theorem to get the magnitude, and we get square root of 109. You could find a decimal approximate, or you can just leave it like that. We do tan inverse, and the calculator gives us a negative answer. Because remember, when tangent has a negative ratio, it returns a negative angle in quadrant 4. So this is where we want to look at the problem. And since this problem has a movement to the right and down, that would tell me that I'm in quadrant 4. Therefore, I need to take that negative angle that's down here in quadrant 4 and add 360 to it to get its correct direction. All right, in this part at the bottom of the page, we are talking about unit vectors. And think of unit vectors as a way of describing how many steps you move to the right or left and how much you move up or down. So if I were to take a look at this vector v in example 3, I move left 3 and up 14. So I could describe this as -3 times my horizontal movement plus 14 times my vertical movement. And since a movement horizontally is equal to I and a movement vertically is equal to j, I would simply describe this as -3i plus j. If we look at number 4, same idea. We want to write w. We have our vector written in terms of horizontal and vertical movement, and we want to write it in typical vector notation. So when we see this 5, that means I move 5 to the right, and when we see this -3, it means I move 3 down. And so these would be our answers to examples 3 and 4. When we're working with basic operations on vectors, we can go ahead and multiply them by scalar quantities. Now when we multiply by scalar quantities, we basically take the entire vector and just make it twice as long, 3 times as long, and so forth. If we see a negative sign in front of it, it means that we draw the head of the arrow on the other side. So for example, to draw 2 times vector v, we would essentially draw one vector v and then another vector v. An easy way to do this is to actually trace over the vector and then copy and paste it using Notability. For -3 times vector v, we're going to draw that same vector, but now we draw 3 of them, and we draw them going in the opposite direction. You'll notice that the opposite vector is still parallel to the regular vector, just has the head in a different way. And similarly, if we want to do negative of vector w, we'll take a look at vector w and draw the arrow going in the opposite direction. Now, when we do vector addition and subtraction, we are going to do what is called adding of head to tail. So when we add vectors, we add head to tail. So let's say, for example, I drew a vector v, and vector v looked like this, and then I want to add this to vector w. When I add it, I need to make sure that I go head to tail. This right here is the head, and this right here is the tail. Now what we see here are the two different vectors, but to actually add them, I have to go starting at the tail of one to the head of the other would end up looking like this. And this right here would be my overall v plus w vector. Now, if we take a look at question E, in question E we're doing E minus w. So v minus w would be the same as v plus negative of vector w. So we're first going to draw regular vector v, and regular vector v, again, looked approximately like this. And then we're going to add it to the opposite of vector w. Well, since vector w was pointing down to the right before, it's going to have the same length or magnitude, but the arrow is going to point up to the right. So it would end up looking something like this. So this is my v, and this is my opposite w, and therefore my resultant, or what I get when I add the two together, is going to look like this. So this is v minus w. So we call the sum of two vectors the resultant. And basically you could think of it like it is the result vector after doing the addition. In this last section we are given two vectors and we are given the magnitudes of them. Recall that this notation means magnitude, and the magnitude is the same as the length of the vector. So since vector v has a larger magnitude than vector u, it will look longer. Now what we are supposed to do is draw the two vectors with this given angle in between them. We are not told the direction of vectors u or w. So what I typically do is draw the longer one on the horizontal, and then I draw approximately a 28-degree angle, and that would be my shorter one. At this point, if we take a look at the directions, we want to find the resultant vector. So again, the resultant vector is when the two vectors are added together. Now right now when we look at it, the vectors are tail to tail. And to add them, we want to make them head to tail. So what we're going to do is we are going to copy vector v up here. So this is a copy of vector v. And then we can go ahead and draw all the way across the resultant vector. So this is u plus v. So this right here is our resultant vector for the problem. Now, one thing you might be noticing here is that the shape looks like a parallelogram. And so another way, an alternate way to find the resultant is to add the vectors tail to tail. Okay, try this last example and then unpause the video when you're done to see if you did it correctly. As you can see, this diagram looks very similar to question A. The key points to note are that we have our vectors v and u, and again, you can organize them however you like. Like I said, I typically put the longer one on the bottom, and then when you draw your resultant vector, you can either copy this vector u up top and then draw head to tail, or you can draw the two vectors tail to tail and essentially complete the parallelogram. All right, that's it for tonight. Homework is Math Excel.